workshop. Our first speaker will be Bill Goldman from the University of Maryland, who has kindly written his title on the board. Will talk to us about group actions and cohomology. Oh no, that's the name. Sorry, the dynamics.
I'm not going to talk about that.
Classifying geometric structures.
Okay. Can everybody hear me? Is this okay? Well, thank you. Thank you very much for the invitation to speak here. It's always nice to be back at the, the Newton Institute. What I'd like to talk about today is a general program for understanding classification of various kinds of geometric structures, such as locally homogeneous geometric structures, or Ehresmann-Thurston structures, GX structures, or equivalently flat connections, or equivalently representations of fundamental groups and character varieties. But I think I'll try to motivate it by discussing geometries. So the first half of the talk will discuss a general program for analyzing the dynamics of the classification motivated by these classification problems. The second part of the talk will give rise to some examples which correspond to, say, the character variety, the SL2 character variety of the free group of rank 2, which is maybe the one place where there's most complete information, and discuss very interesting dynamics on cubic surfaces defined by equations like that. So that's what I plan to do in the second half of the talk. So the motivation, as I mentioned, is classifying geometries on manifolds that are modeled on a fixed kind of geometry. So for example, a Euclidean structure is a geometric structure modeled on Euclidean space and with coordinate changes lying in the group of Euclidean isometries. So following the Erlanger program of Lie and Klein, a geometry will be basically a homogeneous space of a Lie group by a closed subgroup. The general program was initiated in 1936 by Charles Ehresmann, who proposed, given a homogeneous space, look at all the different ways of putting that geometry on a fixed topology. So one example, which whenever I try to explain what I do to non-mathematicians, I give the example of the fact that the two-sphere has no Euclidean structure. So there's no metrically accurate world atlas that has a Euclidean geometry defined consistently on the different pages of the atlas. So I'll fix the topology S, which for most of the talk will be a compact surface, possibly with boundary, and a homogeneous space X with a transitive action of G. And the analogous to the Teichmuller space, there will be a deformation space of GX structures on the fixed topology S upon which the mapping class group will be acting. And one motivation for this subject is that this is a way of getting spaces with interesting actions of the mapping class group and representations of the mapping class group. Closely related is the space of representations of the fundamental group of S, the topology, into the Lie group G. This I will denote by rep pi 1 of SG, the space of equivalence classes of representations, which in general is not that nice a space, but it can be repaired in to make it into a manifold or stratified into manifolds. And the in the case when S is a compact surface with non-empty boundary, then the fundamental group will be free, and this corresponds to very interesting actions of outer automorphisms of free groups on the character varieties into G. So the second half of the talk will describe that in some detail. Another approach, which I won't emphasize here, is that we can think of the space of equivalence class of representations as being flat connections or flat G bundles over S, and the equivalence relation coming from the mapping class group will be gauge transformations covering diffeomorphisms of S. So a more familiar analog, and historically earlier, even though in some sense it seems much harder, is the Riemann moduli space, which parametrizes Riemann surfaces of a fixed topology. Now it is known that the Riemann moduli space is a quasi-projective variety over the complex numbers. It has singularities which correspond to Riemann surfaces with non-trivial automorphisms. So it's, in a natural sense, an orbifold. And later it was realized that you can think of that as a quotient space by the mapping class group of the Teichmuller space, where you include some extra topological information, a marking, so like a topological coordinate system. And this is very important. A marking will be a map from the fixed topology S into the space that has some extra structure, in this case a Riemann surface. The Riemann surface varies, the topology S remains fixed, but we keep track of the homotopy class of F. This defines a natural equivalence relation, which I won't write down, and the space of marked Riemann surfaces forms a Teichmuller space, which is a nice complex manifold, which is homeomorphic to a cell, and the equivalence relation of changing the marking corresponds to the action of the mapping class group. So the Riemann moduli space is the Teichmuller space modulo the mapping class group. So let me go back to the GX structures of Ehresmann and later Thurston. We start with a homogeneous space which will carry a fixed geometry, such as Euclidean geometry or hyperbolic geometry. We fix the topologic manifold S, a covering space in its fundamental group. We fix a labeling, a marking. And then the geometric structure will be defined by a system of coordinate patches, an atlas of open sets, defining and charts mapping into X, so the local geometry of X is transplanted back to U, and on overlapping patches, the coordinate changes or transformations coming from the fixed Lie group G. Now, this is where the subject diverges from the theory of Riemann surfaces, because the coordinate patches, the coordinate charts can be analytically continued in a very strong way to give a map defined on the whole universal covering of S. And this is a local diffeomorphism, a local homeomorphism in every coordinate patch, and the universal cover then develops into X. The deck transformations are automorphisms, and they are represented by compositions of the local coordinate changes and define a map, a homomorphism from the fundamental group of S into G. So this is where the subject diverges from Riemann surfaces. If we knew that there was a strong continuation of local bihomomorphisms to global maps, we could prove, say, that the Riemann sphere doesn't have a complex structure. So in this subject, the fundamental group and universal covering space play a very significant role. So the development globalizes the coordinate charts, the holonomy globalizes the coordinate changes. So many of the ideas go back to Ehresmann, even though maybe not so explicitly. But in trying to classify them, similar to the classification by Teichmuller space of Riemann surfaces, we want to define a deformation space of marked GX structures on X up to an appropriate equivalence relation. And that map will map by holonomy into the space of equivalence classes of homomorphisms of the fundamental group of G. And it was, as I mentioned, this space is actually not so nice. Everything that could go wrong can go wrong in certain cases. The space of homomorphisms into G, if G is an algebraic matrix group, is a real algebraic set and stratifies into smooth manifolds. The action is algebraic, but the group is not compact and the action is not proper, and the quotient is generally non-Hausdorff. And that all these facts are true for the deformation space of structures as well. And the fact that this map, once you put an appropriate topology on this space, is a local diffeomorphism or a local homeomorphism, and in certain cases was first observed by Thurston in the late 70s. So, maybe the first case where this was done was in the case of when G is PSL2R and the deformation space is hyperbolic surfaces, and this was studied by André Weil around 1960. Similar ideas. Changing the marking corresponds to the action of the out of pi 1 of S on this representation space, and the mapping class group acting on the deformation space of geometric structures. So these are the objects that I want to study, and in many cases, just the algebraic problem of studying the space of homomorphisms can be profitably understood in terms of thinking of geometric structures. Okay. So let me first start with a familiar case where the dynamics is not very interesting, but the moduli space is. This is the case studied by André Weil. X is the hyperbolic plane, and G is its group of isometries. The deformation space is sometimes called the Fricka space, which is isomorphic to the Teichmuller space by the uniformization theorem. But in many cases, as I'll describe in a moment, we want to be able to study the space of representations as you change the complex structure on the manifold. And for that reason, I want to really isolate these, because the uniformization theorem is a highly non-trivial theorem and should be appropriately respected. So it's classically known that the holonomy embeds the Fricka space inside as a connected component in the representation variety, and the action of the mapping class group is just the action of the mapping class group on Teichmuller space, which is properly discontinuous. The quotient identifies with the Riemann moduli space I mentioned before. And so when the topology is the torus, then the deformation space is the upper half plane. These are lattices. A marked lattice is just a basis of a vector space, and it's known that the deformation space is naturally the upper half plane, and the mapping class group, which is GL2Z, is acting by linear fractional transformations in this standard way. So this is a familiar picture of the tessellation corresponding to the action of the modular group. So the moduli space, the quotient, would just be the fundamental domain, one of these hyperbolic triangles. So this is a case where the dynamics is not very interesting. It's a nice proper action. But in contrast, if you look at complete affine structures, like Michel was describing yesterday, these are quotients of the plane by properly discontinuous groups of affine transformations, then even in the torus you get some highly non-trivial dynamics. And so Oliver Bowes proved that the space of the deformation space is homeomorphic to the plane. Just the fact that it's Hausdorff is, I found, surprising. But now the action of the mapping class is the usual linear action on GL2Z. And this is a very chaotic action where almost every orbit is dense. Examples of these structures are interesting, and this gives rise to one of the questions that was raised yesterday, Michel's talk, that typically these manifolds will not have any pure translations in their holonomy group. And they arise as follows. These were first discovered by Kuiper, I believe. They, first of all the Euclidean structures. Up to isometry, the Euclidean structures form the upper half plane with a rich geometry, but any two Euclidean structures, any two lattices are equivalent by linear transformations, by a change of basis matrix. So the Euclidean structures all correspond to one point in the deformation space. The other ones are obtained by conjugating by a polynomial diffeomorphism like this. It's quadratic. And the effect of conjugating, say, a lattice by this diffeomorphism would take the straight lines into arcs of parabolas. In this case, we have a pure horizontal translation, which is conjugated to a translation. But for the typical lattice, I think I have a picture here. Yeah, typical lattice like this one, there will not be any translations in the holonomic group. So this is a nice exercise to show that if you conjugate a translation by this quadratic polynomial, the quadratic terms cancel out, but you're left with a cross term, and you get a group of affine transformations like this. In any case, one can parametrize this, the equivalence classes, and obtain R2 with the usual linear action of GL2Z on it. So it preserves the Euclidean area on the plane. The action is ergodic. This follows from a very general ergodicity theorem of Calvin-Moore. For example, one consequence is that almost every orbit is dense. So ergodic means that every invariant measurable set is either full measure or is either zero measure or its complement has zero measure. The last statement.
Same thing for n torus?
Yes. It's much more general. So GL2Z is a lattice inside GL2R or SL2R, and if you have a lattice acting on a homogeneous space where the isotropy group is non-compact, more proves ergodicity under maybe some mild assumptions. It's very general.
No, but I meant the same thing about the deformation space as Rn or something.
I don't think so. I don't think it's really been worked out. It's pretty complicated. It's not an easy algebraic problem because it involves quotient by unipotent groups. So, the usual machinery of geometric invariant theory is not available. So the proof that we know is pretty nitty-gritty. Okay. So I want to propose that the classification, because we can't form nice quotient spaces, should really be treated as a dynamical system. And the dynamical systems that arise are actually quite interesting in their own right. So let me say a little bit about some of the ideas that go into studying this. Let me assume that S is a closed surface or a compact surface. And if G is a Lie group whose adjoint representation preserves a non-degenerate symmetric bilinear form on its Lie algebra, then one gets a symplectic structure on the space of equivalence classes of representations. When G is SL2R, then, as I mentioned, the Fricka space of hyperbolic structures, which identifies with Teichmüller space, is a component of the space, and the Weil-Petersen Kähler structure, the Kähler form, is a special case of this general construction. When G is compact, for example, the circle, in that case, the space of representations is a torus with a nice symplectic structure. But when you put a complex structure on S, you make it into a Riemann surface, then this identifies with the Jacobi variety. And that's now a nice abelian variety with a Kähler structure, and that structure itself parametrizes the Riemann surface. When for higher n for the unitary group, then this was extended to a moduli space of semi-stable holomorphic vector bundles over Riemann surfaces in important work by Narasimha and Seshadri, and later interpreted in terms of gauge theory by Atiyah and Bott. When the boundary of S is non-empty, then the representation variety is oftentimes odd-dimensional, can't be symplectic. But if you look at the restriction map to the boundary, its fibers are all symplectic manifolds, and this is a case of a Poisson structure where the functions have a natural Poisson bracket. And since I want to talk about surfaces with boundary later, I'll be describing this geometry in detail. So the case that isn't so important for geometric structures but still quite interesting is when G is a compact Lie group. The components of the representations correspond to the elements in the fundamental group of the commutator subgroup, or the maximal semi-simple subgroup. And then, in that case, on each connected component, which I'll label this way, the mapping class group has a nice ergodic action with respect to the measure coming from the symplectic structure. So this was first proved for the groups with SU2 factors by myself, and then proved in general by Pickrell and Zia for arbitrary compact Lie groups. This gives rise to a unitary representation on the L2 functions on the representation variety. And this was, in fact, this is something I learned from David Fisher, that the only finite dimensional invariant subspaces are the constants in the space, and this is the condition of weak mixing. And these ideas will come up a lot, and it's sort of a formal consequence, because once you know it for a Lie group G, and it's Cartesian square, then weak mixing is equivalent to the ergodicity on the square of the action. So you can take that as the definition. It's also equivalent, and this is used in the proof of later, that's equivalent to saying that the product with any ergodic action is also ergodic. So this is a very nice spectral invariant, which is stronger than ergodicity. So the general program, which I began recently with my colleague at Maryland, Giovanni Forni, is to try to use Teichmuller dynamics to get sharper dynamical information about these actions. So we'd like to replace the dynamics of the mapping class group, which is a discrete object but rather rich and complicated group, by something simpler, like the additive group of real numbers. And so we'd like to find some continuous object that, whose dynamics mirrors the discrete object, the mapping class group action on the moduli spaces. And so we'd like to, say, vary the Riemann surface and then take this object, the symplectic variety, and see how it varies as you change the complex structure. So like the classical theory of Jacobians over the space of Riemann surfaces, you have lots of extra structure, and this maybe began by Narasimhan and Seshadri, and then in Nigel Hitchens' paper on Higgs bundles and SL2C, elaborated quite a bit. In fact, the representation variety when G is compact will get a Kähler structure for the fixed symplectic structure. When G is complex, then you get a stronger hyper-Kähler structure, which is like a quaternionic an integrable quaternionic structure over the space. So when we take the product of this with the Teichmuller space, the fibers have a varying geometry, which is quite interesting, but I won't say much about it. Okay, so as I mentioned, I want to take the Teichmuller space and take the product with the character variety, or fixed component, and then quotient by the mapping class group. And that will be a fiber bundle whose fiber is the representation space over the quotient, which identifies with the Riemann moduli space. So this is why I want to distinguish Fricka space from Teichmuller space, for example. So this is a standard construction of a flat bundle, and then the leaves of the horizontal foliation given by the fibers that look like Teichmuller spaces, these leaves then correspond to the orbit of the mapping class group on the character variety. So this is the first attempt to get a continuous object whose dynamics mirrors the action of the mapping class group. Okay. but it's a foliation which is still not as tractable as an action of a connected Lie group. So this foliation contains a nice action. The leaves are copies of the Teichmuller space, and if we promote this not just to the Teichmuller space, but rather the Teichmuller unit sphere bundle, and look at the
That's representations of phi to g and subscripts of tau means the tangent space?
no, the tau index is the component. So I want to get a, I want to state an ergodicity result, so I want to work on each connected component. And so these are labeled by the fundamental group of the commutator subgroup of G. So now I work over the unit tangent bundle of Teichmuller space with the Teichmuller metric, and I quotient by the mapping class group to get the moduli space. Then this unit tangent bundle is stratified into subspaces. The tangent space corresponds to holomorphic quadratic differentials, and the type of the divisor of the holomorphic quadratic differential defines various strata, which will all be invariant under the geodesic flow. In fact, this is part of a larger action of SL2R, where the flow is just the diagonal matrices inside SL2R, and those will even vary the strata. And the strata are generally not connected, so we work over a fixed component of the strata. Okay, so this is the setup now that we're going to work over this space, the unit moduli space, and again form a flat bundle whose fiber is the character variety, or the deformation space of geometric structures. So here's the notation indexed by the components of the strata and the components of the representation. And now we can lift the flow from the Teichmuller geodesic flow from the unit tangent bundle of Teichmuller space to the to this flat bundle. And that gives a flow. In fact, it gives an SL2R action. And now we can extend the dynamics on this unit tangent bundle of the moduli space to this flat bundle. And this is a more satisfactory continuous version because now we're dealing with actions of R or SL2R. And so the observation that Giovanni and I made was by combining a lot of these results that were already known, such as the ergodicity of the mapping class group, as well as known results in dynamics and representation theory, this extended Teichmuller flow is strongly mixing on each one of these components. So there are a lot of results. One key point is that if you have a flow that is mixing or ergodic and it lies inside an SL2R action, another theorem of Calvin-Moore implies that the flow is strongly mixing. So one of the ingredients is the proof of ergodicity of the mapping class group, which strongly uses the fact that the mapping class group is generated by contains Dane twists, which I'd like to get away from, but I'll explain some of the ideas. So I'm hoping that that using deep results in Teichmuller dynamics will give sharper results on the dynamics of the mapping class group. Okay, so let me say a little bit about the proof of the ergodicity and then get into some specific examples for free group of rank 2. If we have a element in the fundamental group, then we can look at, say, the character of that representation to give a function on this space. And functions on a symplectic manifold define Hamiltonian flows. And so the invariant functions, such as the trace, when we apply them to elements, will give vector fields. And these are interesting in their own right. My own introduction to this subject was trying to understand Scott Wolpert's work on Hamiltonian flows on the Teichmuller space with the Weil-Petersen metric, which I think should really be called Weil-Petersen space, as a symplectic manifold, and he showed that if you take f to be the length function, which is essentially equivalent to the trace, you get the Fenchel-Nielsen twist flow. So you imagine taking a hyperbolic surface, a simple closed geodesic, remove that to get an open surface with two boundary components that you identify, and then you re-identify by an element by a rotation of the circle. And this is a pure hyperbolic geometry construction, which is Hamiltonian with respect to the Weil-Petersen-Kähler form. There's a piece of commutative algebra that comes in, and that's that you can find simple closed curves on a surface that for SL2R, their character functions generate the coordinate ring. Now, that's one thing you can do with a simple closed curve on a surface, is to look at the twist flows, but you can also look at elements of the mapping class group, namely Dane twists around them. And the Dane twists around the simple closed curves, in some sense, generate lattices inside these continuous groups of Hamiltonian flows. It's not as nice as you might expect because the parametrization varies with the level. So we're not getting a group that contains the mapping class group in a nice way as a subgroup, but on each orbit. If you have an elliptic element, a simple closed curve whose holonomy is elliptic, then the integral curves are going to be circles. They're going to be a periodic orbit. And for almost every value, this Dane twist will be also a rotation that lies in this, and for almost every value, it'll be a rotation of infinite order. And this is maybe the first example of an ergodic action. And so this is how you go from knowing that an invariant function under the mapping class group is almost everywhere constant. Show that every invariant function under the Dane twist is invariant under the Hamiltonian flow. Now you use the fact from commutative algebra that the simple closed curves give enough functions to generate the coordinate ring of the representation variety, and that immediately leads to the fact that the differentials span every cotangent space at every point. By duality, that means that the vector fields span the tangent space at every point as well. Okay, so that means that the group generated by the flows has open orbits, and since they partition and the space is connected, you get every function is constant. And then more generally, if you know that a simple loop has elliptic holonomy, you can use this argument even if the group is not compact. Okay, so are there any questions? So now I'll move to some specific examples in the second half of the talk. So now I want to specialize to the case of compact surfaces of Euler characteristic -1, which is equivalent to saying that the fundamental group is free of rank 2. And there are four such surfaces. There's the three-hole sphere, the one-hole torus, these are the only two that are orientable, and then the two-hole cross surface or two-hole projective plane, and the one-hole Klein bottle. And at the very end, if I have time, I'd like to describe some interesting phenomena that occur for the one-hole Klein bottle. Okay, so the free group of rank 2 has all kinds of nice properties which lead to a nice theory, but are rather difficult to generalize to higher rank. But the space of representations is just given by pairs of generators. And then we want a quotient by conjugation, simultaneous conjugation by, so we're looking at conjugacy classes of pairs. And this was work first published in, or the earliest reference I know is 1889 by E. Vogt, who showed that these are given by the traces of the two generators in the product. And so I want to think of these as geometrically the two generators might correspond to two boundaries of the three-hole sphere, two boundaries of a pair of pants, and then the product, we don't sometimes think of as Z, is the third boundary component. And this is an isomorphism in the sense of invariant, geometric invariant theory. Any invariant function on this space is given by is a function of these three variables. This can be interpreted geometrically as being an analog, or an algebraic version of the side or angle test for congruence in non-Euclidean trigonometry. The traces will correspond to lengths of sides or angles in a triangle. So we have a complete picture here, and this leads to a really interesting dynamical system because of another special property of a free group of rank 2, and that's that the commutator of the two generators is a, this is the theorem of Nielsen, is taken to itself by an automorphism. Okay? And in SL2, the trace function is conjugacy invariant and also invariant under inversion. And if you work out what the trace of the commutator is in terms of the three traces of generators, you get this really interesting cubic polynomial, which I'm calling kappa. So this is the Casimir function. This is the function that defines the Poisson structure for the surface with boundary. Let's turn this off. And so this is three-dimensional, so it can't be symplectic, but the symplectic leaves are surfaces, and they have an area form, which is invariant. Okay, so I'm going to be looking at the level sets of this function and describing this. So Nielsen's theorem has the effect of saying that the out F2 action is actually the action of the mapping class group when we work with this particular surface. So it's definitely not true for the other three surfaces. The pair of pants basically has a trivial mapping class group. But Nielsen's theorem can be interpreted geometrically as saying that every self-homotopy equivalence of the one-hole torus is homotopic to a homeomorphism. What will be interesting is that even if you just want to work with mapping class groups, you can't escape looking at non-geometric automorphisms of the fundamental group. In particular, you'll get wandering domains for the action corresponding to homotopy equivalences from our fixed topology, S, to other surfaces, like the other three surfaces I mentioned before. I'll say more about this. So the automorphism group, as I mentioned, is quite big. This polynomial is symmetric. It also has some linear automorphisms where you change the signs of two of the variables and keep the other one fixed. That corresponds to lifting from PSL2, which is maybe more natural, geometrically to SL2. So those are not so interesting. On the other hand, there's some involutions that are quite interesting, and these generate most of the modular group. You can see that these are automorphisms very nicely. Take a projection, say the projection into the A to Z coordinates. That means fix eta and zeta. Then this cubic polynomial becomes quadratic, and we get the projection as a branch double cover, and the involutions are deck transformations. It's really easy to see this too. Rewrite the equation this way so that you see that it's a quadratic equation in psi, and if you have one root of the equation, then the other one is just given by taking the linear term and subtracting the first one from that. So that gives one of the involutions. These are polynomial automorphisms of this polynomial. On the other hand, it's an inhomogeneous polynomial, and it doesn't extend to the projective space. It's a very special property of this family of affine varieties. Okay, so we have three involutions corresponding to the three coordinate directions, and they generate a free Coxeter group of rank 2, in other words, a free product of three Z2s. The case of reducible representations is a particularly interesting cubic surface. So when you set the trace of the commutator equal to 2, then you get a picture like this. This has a rational parametrization. The action of the mapping class group actually factors through this. So these would be the eigenvalues of diagonal matrices that have these traces. And this is, again, a homogeneous action where Moore's theorem applies to give interesting dynamics. Here's a level set where a component of the level set where the trace of the commutator is between -2 and 2. When you take the traces, you can't really tell, and if they're real, then you really can't tell whether they're an SL2R or SU2. These are the two real forms. And you get components that are spheres. I drew this in Mathematica, which draws the level sets by the coordinates, which is perfect for this idea, because the level sets of the coordinates are the trace functions. And you can see the transitivity that I mentioned before. Each one of these level sets is an ellipse, and the Dane twist induces an action which is going to be a rotation of the ellipse of varying rotation angle. And remember, the last step in the proof is to show a transitivity. So if it's invariant around the twist in the z-coordinate, then it's going to be in almost everywhere a constant function of z. You do the same thing for x and y, and you can see that these three one-dimensional foliations are transverse. So it suggests the ergodicity on this action, on this component. Okay, so one can explicitly write this down. I'm particularly interested in the case of SL2R, and as I mentioned, that sometimes you'll get hyperbolic structures on the one-hole torus and on the three-hole sphere. In the case of the three-hole sphere, the Vogt-Fricker theorem gives a statement that hyperbolic structures are parametrized by the lengths of the boundary, and in terms of trace coordinates, that corresponds to the octet, where all three coordinates are less than -2. The trace of the commutator is greater than or equal to 18, and the minimum is achieved when these are all -2, which is a particularly interesting case because that corresponds to the hyperbolic structure, the complete hyperbolic structure on a three-punctured sphere. So it's a union of two ideal triangles. So the dynamics is quite different between 18 and, when it's greater than 18 and less than 18. In particular, if you have a homotopy equivalence from the one-hole torus, our fixed topology, to a three-hole sphere or other surfaces, then you get nice spaces which are going to be permuted. The mapping class group of this new surface will be acting on it, and the other elements, the self-homotopy equivalences, which are not geometric, will be permuting these domains around. You get wandering domains. One case that's particularly interesting, I'll just very quickly mention this since I'm a bit pressed for time, and was the Markov surface corresponding to the Markov triples. These are hyperbolic structures on the punctured torus with triple symmetry. And this is an interesting Diophantine equation, and this led to a conjecture. And so I think Brian Bowditch was saying yesterday that this led to a nice theory, and which he was using in a paper which is very important in the subject on quasi-Fuchsian groups and trace coordinates. It leads to some of the things I'll be talking about in a moment. And in this case, you have an isolated point, the origin, which corresponds to an SU2 representation. It's a fixed point, and then each of these corresponds to the Teichmuller space of the one punctured torus. So, as I mentioned, let's look. This is a picture of what the topology looks like when k is greater than 18, or greater than 2. I'll show a little movie of how the level sets change after I describe this text. And in this case, we get maps from the Fricka space with fixed commutator into the level set. And these would be triangles, which I unfortunately haven't gotten around to programming in, but should be quite an interesting picture. When the trace of the commutator is less than 18 and greater than 2, the action is ergodic, and on the complement of these wandering domains, the action is ergodic using the fact about elliptic elements. So this is a trace reduction algorithm that goes into proving these things, to use elements of the mapping class group to move down into elements where simple closed curves become elliptic. Okay, so the last example I give before I show what the movie of the level sets is the Fricka space for the one-hole Klein bottle. In that case, I'm going to take x and y not to be real, but rather purely imaginary. That corresponds to purely imaginary matrices in SL2C correspond to orientation reversing isometries of the hyperbolic plane. And making a change of coordinates, you get these real algebraic sets, and they look like this. And the projection to the plane is a diffeomorphism. Okay, so the next picture will be drawn in the plane. The reason I find this particularly interesting is that in none of these ones there are simple closed curves elliptic, but you still get interesting dynamics. And the level set looks like this, and then using some of the ideas in Brian's paper, we can show that there's a nice region of discontinuity that correspond to these triangles. These are all invariant under the mapping class group of the one-hole Klein bottle, which is virtually cyclic. Z is going to be the product of the two orientation reversing generators, so Z will have real trace and be orientation preserving. Each of these components are all going to be indexed by the modular group, the cosets of this mapping class group inside the modular group, and you get wandering domains. The complement looks extremely interesting. We know that it's closed and nowhere dense. It would be nice to know whether it's a full measure or, more generally, to be able to compute its Hausdorff dimension. And so this is in a paper that was recently finished, joint paper with George Stanchev, Serpio Tan, and Greg McShane, that discusses this case. So this would be one case where one has to use ideas other than the generation by Dane twist. Okay, so in the remaining time, I'd like to show you the level sets of this cubic polynomial. So remember, this is x squared plus y squared plus z squared. So C is the commutator trace, and in this picture it's around -2. So the highest order term is x, y, z in this. So out near infinity, this looks like x, y, z equals 0, which is the union of the three coordinate planes. So you're always going to see four ends. And this will correspond to hyperbolic structures on the one-hole torus. For -2, it's actually with a cusp. And the mapping class group is the full modular group, and it's acting properly discontinuously on each quotient. Now C starts to increase. So here it is at -1, and you can see that there's now a compact component, which was the point when C was -2, and this corresponds to the family of SU2 representations. Again, now these would correspond to hyperbolic structures with cone angles at a single point, and the action is still proper here. And this behavior persists until you get up to to 2, the Cayley cubic. And that's, so right before that, the compact blob of, down here, of SU2 representations gets bigger, and the coned hyperbolic structures on the torus move in, and when you get to the point of the reducible representations, no, I didn't want to do that. You get down to them SO2. So this is the Cayley cubic, which you can think of very nicely as a rounded out tetrahedron, a pillowcase with these 4 wings coming out. The 4 wings correspond to diagonal real representations, and these correspond to representations in SO2. So the 2 real forms of C star, positive reals and the unit circle. Okay, so since I'm in England, I can talk about the 27 lines on the cubic surface. And up to now, all the lines are purely imaginary. Here we get the diagonals, and you get 6 lines, but each is counted with multiplicity 4, which you can see very nicely by going to the next increment. Now these 5 components connect up. We've passed a critical point, and you can see that each of these diagonal lines on the tetrahedron split into a family of 4 lines. So I'm going to keep increasing this to show you where the wandering domain is. So there are 3 lines at infinity, and there are 27 lines, and then the remaining 24 lines are grouped into three families of 8. So I'm going to concentrate on this piece right here. There's a little triangle here, and as we keep increasing the value, fortunately it doesn't refresh very quickly. Let me get close to 18. Okay, now these 3 lines in here are getting very close together, and at the value of 18, they concur. They all pass through a point. So this is a special cubic surface that was discovered by Clebsch, and this is called an Eckart point in the literature. This is the point that corresponds to the complete hyperbolic structure on the thrice punctured sphere, -2, -2, -2. And the action is still ergodic, but now we have this distinguished point, a distinguished orbit. Now I'll increase it a little bit and move this around a bit. You can now this is opened up into a triangle, and this is the triangle that generates the wandering domain. So so this corresponds to hyperbolic structures on a 3-hole sphere, where the commutator curve, which is a curve that intersects itself 3 times, has a fixed length, which is sort of never seen a construction like this before, and that will be wandering under the action. The complement of this orbit will now have a chaotic action, and I would really love to know how long it takes under using these generating involutions to get back close to this triangle. The images of the triangle are going to be triangles, but now with curved sides, because the polynomial is a very high degree. Okay, so I hope I've encouraged you to be fascinated by this dynamical system. Yes, John?
I was supposed to imagine there's lots of triangles in that picture, the orbit of that triangle. There will be 4 triangles like this. If you try to turn this thing around, that are actually linear triangles. But is this, you're saying there's a wandering domain?
Right.
Triangle. So the mapping class group would take this triangle to other
curvilinear triangles.
Curvilinear triangles, which are not drawn.
That's right. And
we could ask you to draw it for the next lecture.
Yeah. Well, okay, that's a good challenge. Because I'd really love to do this, but I have.
Oh, I see. You're just waiting to be asked.
Yeah. Right.
Perfect.
Yeah. Okay. Anyway, thank you.
Other questions?
This pattern of lines is not invariant under the out of 2 axis.
That's right. That's right. I mean, the subject is very rich. If you go to the projective space, the collection of lines has its own automorphism group, which is connected to
the vital group of E6, but it doesn't preserve this structure. And the mapping class group action is only acting, it's acting on the affine cubic, so it doesn't, yeah. So there's some very nice work of Serge Cantat and Frank Lorrain on this action. And they can show that if you, on the SL2C character variety, which is much more complicated, that you can find an orbit that both accumulates at the origin, in the SU2 representation I told you about, as well as the boundary, the quasi-Fuchsian representations. But none of this preserves the structure at infinity. And so the compactifying this is quite interesting too, because you get lots of different compactifications by different different mapping classes. Polynomials grow, the degrees grow very quickly, very fast.
Okay, let's thank the speaker.